Hello everybody. Today I'll describe you and I'll show you how geometric sequence or geometric progression, both of the terms mean the same, works, and I'm just going to show you and prove the formulas you have seen that are connected with this topic. And I think the best way to describe it is to give you an example of a geometric sequence. So let's have 1, 3, 9, 27, 81, and so on, so on. And you can see what is connecting all of these terms. Well, you multiply the previous term by 3 and you get the next term, and so on. So if we multiply this by 3, we get 3. If we multiply this by 3, we get 9, and so on, so on. And that's basically what a geometric sequence is. The ratio of two consecutive terms should be the same in each for each term we use. So let's say we divide 3 by 1. All right, so that's consecutive terms, one first term and second term. And let's have 81 over 27. And if that is fulfilled for every term, then that's a geometric series. So let's see, it's 3 equals 3. Alright, so correct. And what we call this ratio is, we just call it common ratio, and we denote it as R. So R equals 3 in this case, because we multiply this by 3 and again by 3, so it's just a common ratio. And now that we know that, let's try to find the formula for the nth term, for the un. And I'm not gonna give you a formal proof of it because I think it's quite visible after I show you this. So u1 is, for this case, it's 1. Right? Well then, u2 is 1 times 3. u3 equals 1 times 3 times 3, because we multiplied again. u4 equals 1 times 3 times 3 times 3. Well, that's equal 1 times 3. That equals 1 times 3 to the second. 1 times 3 to the third. And I think it's quite obvious that un equals 1 times 3 to n minus 1 for this particular series. But we know that 1 is u1, so un is equal u1 times, and 3 is the common ratio, so r to n minus 1. So that's the nth term of a geometric series. So, and it works for any term. I mean, n is not equal 0, and it's bigger than 0 basically, and it's natural. But yeah, okay. So now that we have the nth term, let's think about the sum. About the sum of all of these terms, right? So we denote the sum as in arithmetic sequence Sn, and Sn is u1 plus u2 plus u3 and so on, so on, so on. That's equal to u1 plus u1 times r. We already know that. The second term is u1 times r plus u1 times r squared plus u1 times r to the third, so on, until u1 times r to n minus 1, because that's the nth term. So that's the last term for n. Okay, so now we can multiply the Sn by r. So r Sn is equal to u1 r plus u1 r squared plus u1 r to the third plus u1 r to the fourth, so on, u1 times r to the n. And now what we can do, we can actually subtract from this Sn. So we have r minus 1 Sn equal to, well, that cancels this cancels this, and so on, so on, so on. And all that we have left is u1 times Rn, so u1 times Rn. That's not subtracted because this is the last term, minus u1 from this, because we subtract. So Sn times r minus 1 is equal to u1 times r to the n minus 1. And now we can divide it by r minus 1. So it's u1 r to the n minus 1 over r minus 1. And it's quite popular that we take the minus from here in front of the bracket and minus from here in front of the bracket. That's the more popular formula that you can encounter. So that's that over minus 1 minus r. And well, these cancel out, so that's the most basic formula for the sum, and you probably have seen it a lot of times. So that's the formula for the sum to the n. And now there is a way of calculating, there are sums that go to infinity and actually go to a number. That might sound a bit weird to you, but I'm gonna give you an example. Let's say we have a series 1 plus, and 1 second, 1 fourth, 1 eighth, 1 16th, and well, that tends to infinity. Okay, so our first term u1 is obviously 1, and let's calculate the ratio. I mean, it's quite obvious that the ratio is 1 over 2, but just to show you that you can, if you don't see it, you can actually calculate it. 1 over 2 over 1 is equal to 1 over 8 over 1 over 4. So we have 1 over 2 equals 1 over 2. You don't even have to do that. I mean, you just have to divide one term by the previous term, and that's what the common ratio is, and it's obviously 1 over 2. That's what we got here. And so ratio is 1 over 2. So now let's plug in the sum. So Sn equals u1 1 times 1 over 2 to the n minus 1 over sorry, I used this formula, but 1 times 1 minus 1 over 2 to the n over 1 minus 1 over 2. Alright, so now let's say n tends to infinity. So what happens when n tends to infinity? Okay, so n only affects this, this little part. So what happens if we take 1 over 2 to infinity? Okay, and I mean, it might be a little bit of a stretch, but when you have a limit, okay, it's gonna be easier if we have just 1 over 2 to the n. So if n is getting bigger and bigger and bigger, then it's, you know, it's 1 over 2, but then, you know, the next one is 1 over 4, the next one is 1 over 8, the next one is 1 over 16, and the further it goes, the closer it is to 0. So we actually assume it is 0. I mean, if it tends to infinity, then it's most likely going, you know, 1 over 2, 1 over 2, 4, and so on, until it goes to 0. So Sn is actually equal to Sn, where n tends to infinity. So that's just, I think that's informal, and that's not how you should write it. It's just S 1 times 1 minus 0 over 1 over 2, and that's 2. Huh. It might be quite surprising for you, because you know, you add 1 over 2, you add 1 over 4, you add 1 over 8, and you suddenly come up with 2. So the sum of this series to infinity is 2. Well, that's quite surprising, but it's the truth. And also, now I gave you an example of a sum that goes to infinity, but basically, any sum, arithmetic sequence, where the common ratio is bigger than -1, but smaller than 1, not equal to, then it actually tends to a certain number. And I mean, and it's quite obvious, because what we have here between -1 and 1 is our you know, 1 over 3, so we have 1 over 4, I don't know, 1 over 6, and when you put these into to n that tends to infinity, then you know, you get smaller and smaller. So all of the fractions are hidden here, even the negative fractions, because even if it's negative, I mean -0, what's that? So we don't even have to worry about if infinity is even or not. I mean, it's not even a number, so it's really hard to say, but it doesn't really matter if it's minus or if it's a plus, because it will always tend to infinity, which is basically 0. So yeah, I mean, it's quite interesting, and I think yeah, I think that's about it about the geometric sequence. And yeah, thanks for watching.